Okay, today we are going to study birth and death process. Uh, Actually, we're going to study three variants of these things. Okay, so first, birth process. So, so in this process, let's say, each cells can born or something can born. So the number of some individuals can only increase. So birth process, and then next we consider death processes. So in which individuals can only die, so nothing is born, they only die gradually. And then we consider the combination of the two. So they can both can be born or die, birth and death. So depending on some conditions, the rate of birth, the rate of death, the population can increase or decrease. It depends. So these are somehow similar to the Poisson process, but there are some important differences. So let's start. Okay, let's start with the birth process, which is also known as the Yule process. I think this Yule is some mathematician or someone, which I'm not sure. But anyway, this can be best explained by an example of the colony of bacteria. So if you consider a dish where we grow bacteria, each bacteria can split into two bacteria. Each bacterium can split into two bacteria by cell division. Okay, so this bacteria is gone and it becomes two bacteria. So this can happen with certain probability. Let's say within unit time, the rate of cell division is lambda, let's say. So within a duration of time, let's say delta t, the probability of cell division is lambda t, lambda delta t. Okay, so we take this delta t to be very small, so that within this duration of time, at most one bacterium can split into two. Okay, so no two bacteria divides at the same time within this amount of time. So, I mean, at least this probability can be negligible, should be negligible. Okay. So here's the scenario. We first start from time t equal to 0, where the number of bacteria at this time, which is denoted by this n of t, is some number, so nt. Okay, and after the probability that an individual cell can divide is given by this lambda times delta t, where delta t is a small positive real number and lambda t is also a positive real number. And this lambda is the birth rate. So if there are n cells, so this is the probability of one cell dividing. Okay, so if there are n cells, the probability that any one of the cell divides is given by lambda times n times delta t. Okay, and we assume that the probability that any two cells divides within the same duration delta t is negligible. So that probability should be denoted by small o and delta t. Okay, so this means this quantity is higher order of delta t, like delta t squared, delta t cubed, and so on. So that compared to this rate, this term is negligible. Okay, So the probability that a cell divides, uh, that cells divide cells division is lambda n delta t plus small o delta t. So no cell divide, the probability that no cell division is 1 minus this, okay? And O delta t, okay? And so we want to calculate this probability. The number of cells at time t is equal to n. So let's denote this probability by Pn of t. So we want to find out this probability. So what is this? And the initial condition is this P n0 of 0 is 1. So at time t there are n0 cells, and consequently at time t equal to 0, if n is greater than n0, then this probability is 0. Okay, so that's the probability. Okay, this can be summarized. This can be summarized in this way. So Pn of t is equal to delta. So this is Kronecker's delta, and 1 and t. Okay. By the way, this is Kronecker's delta. So Kronecker's delta, which means n and 0 is 1 if this n is equal to n0. Otherwise, it's 0. And this one is called indicator function. So let's see. A is a set, and x is equal to 1 if x is in A. Otherwise, 0. So in this case, if t belongs to so initial condition. So if t belongs to this set is the set containing only one number, which is 0. So if t belongs to this set, that means t is equal to 0. Then this is 1. Otherwise, it's 0. Okay, so this is the initial condition. Okay, so based on these assumptions, let us try to construct some differential difference equation, which should be satisfied by this function, which we want to determine. Okay, so let's see. So at time t plus delta t, so this is delta t after time t, the probability of that the number of cells is n should be given by this. It was either there were n minus 1 cells at time t, and then one of the cells divided during delta t. So and small o delta t, or there were already n cells at time t, and there were no cell division during delta t. So that is 1 minus lambda n delta t. And all delta t. Right? So this is another application of the partition theorem. So at time t, there are two states. That is, one is there are n minus 1 cells, and then one of the cells divided. Okay, divided. Or there are already n cells, then no cells divided. So that is the state of the system at time t plus delta t. And there are no other cases. Okay. So let's consider this one. Oh, okay. Another one. So this is for n greater than n minus 1. Okay. And when n is equal to n0, then this should be like this. So since there are n0 cells in the beginning, so at time t plus delta t, if there are still n0 cells, that means there were no cell division. So we can ignore this first term in the equation. So we consider only the case where there were no cell division. Okay. So so let's first consider the second one. So if we move distribute this and move one of the terms here and divide everything by delta t, we have this equation. P n0 t plus delta t minus P n0 t over delta t, and that is lambda n0 p n0 t plus or minus something of the order of delta t divided by delta t. So as usual, we take this limit. Then the left-hand side becomes the derivative. And on the right-hand side, we can ignore this term. So it becomes lambda n0 p n0 t. Okay. And if you apply the same procedure to the first equation, this equation, then you should have, I leave the details to you, it's an exercise. So that should be lambda n minus 1 and p n minus 1 t minus lambda n and p n of t. So we have these two equations. So in this, the second case, n should be greater than n0. Okay, so here's the differential difference equation which this probability mass function should satisfy. Okay, now if we solve this, then we should be able to find this the general form of this function. Okay, so let's solve these equations. And there are multiple ways to solve these, but first try the most direct method. So first consider the first equation, and you should immediately see the solution, which, this is a very basic differential equation, so it's very easy to solve, and the result should be some constant times exponential of this lambda n0 times t. Okay, but we have the initial condition, which was 0 equals to 1. So if you substitute t equal to 0, then this should be equal to 1 and c should be equal to 1. Okay, so therefore the solution is this. Okay, when n is equal to n0. Okay, then what? So we substitute this function to this. So next we consider the case when n is equal to n0 plus 1. So we can use the second equation. So that is, to be explicit, dpn0 plus 1 dt and lambda. So n is equal to n0 plus 1. So this should be n0 and 0 here again, and lambda n0 plus 1 p n0 plus 1 of t. Okay, so let's see. We have n0 plus 1 here and here. So let's move this term, the second term, to the left-hand side. So we have this plus lambda n0 plus 1 p n0 plus 1 equal to lambda n0, and we know this solution to be this. So that's exponential of lambda, negative lambda n0 t. And we've seen a similar equation when we were studying the Poisson process. And the way to solve this, I hope you review the previous lecture. First, for example, multiply both sides by the inverse of this, and use the product rule for differentiation, and then integrate both sides, and we should have this. So, and after putting in the initial condition, we should have this 1 minus e negative lambda t. Okay, initial condition for this function is this: p of n0 plus 1 of 0 should be 0. Okay, this is the initial condition. So based on that, we determine all of the constants of integration, and this should be the answer. And you should check. And now that we know this, we can apply the same logic when n is equal to n0 plus 2 and use this differential equation. And for this, you can use this solution and repeat the same process over and over. And then hopefully you will see the pattern, and maybe you can prove by induction, for example. Now, the way we just described to solve this differential difference equation is just fine, but it's kind of tedious. So we explain another approach, which is based on the probability generating function. Okay, so just like we did for the Poisson process. So here's the definition of the probability generating function for this case. That is, as usual, probability mass function times some dummy variable s to the power of n. But in this case, this n varies from n0 to infinity because n0 is the minimum value in this problem. So we multiply both sides of this differential difference equation by s to the power of n. So in the first case, it's s to the power of n0. Second case is s to the power of n and s to the power of n. Then take the summation from n equal to n0 to infinity. So the left hand side becomes like this: dpn0 t s, actually this is n, but we can move the differential operator to the outside of the summation, and that becomes partial differential. So that's this, and Pn of t times s to the power of n. But this is the definition, very definition of this generating function. So what we have here is derivative of g, the PGF, with respect to time. So that's the left hand side. And for the right hand side, let's see. First, let's look at those terms with this negative sign. Okay, so that will be negative lambda sum from n equal to n0 to infinity, and n Pn of t s to the power of n. Okay, now somehow we want to get rid of this n because otherwise we cannot express this term in terms of this PGF. Okay, so here's how we do. Let's look at this, s to the power of n, which is equal to s to the power of n minus 1 times s, and move this s outside of this summation. So that becomes this. Let's write in this order. Not minus 1. T. Okay, then let's see. This part becomes, this is equal to this derivative of s to the power of n with respect to s, right? So this is just right here, summation, and s ds and pnt. Now we can move this differential operator to the outside of the summation, which now becomes partial derivative. And that is s to the power of n and Pn of t. Now this is the PGF. Okay, and then the remaining part is this part. Okay, this times this. Okay, so that is sum over, actually this varies from n plus 1 to infinity because there is no term in the first equation here, only starts from the second equation. So that is lambda n minus 1 and Pn minus 1 of t and s to the power of n. Okay. Now, somehow we want to get rid of this n minus 1 so that we can express this summation in terms of the generating function. For that aim, split this s to the power of n into s to the power of n minus 2 times s squared. Then that and move this s squared outside, and that is n minus 1 and s to the power of n minus 2 and Pn minus 1. And again, this term is this s to the power of n minus 1 differentiated with respect to s. So that is lambda s squared, and move the differential operator outside of the summation. And that's Pn minus 1 and Sn minus 1. But here, summation starts from n0 plus 1. So if we change the variables so that we can sum from n0, then those n minus 1 becomes n. And now, then this is the generating function. So it becomes lambda s squared, derivative of the generating function with respect to s. So after all, on the left hand side we have this, and on the right hand side we have this and this. So after all, if we summarize, we have this differential equation. So the left hand side is the derivative with respect to time, which is equal to lambda s squared and derivative of g of st with respect to s, and minus lambda s derivative of g of st with respect to s. So let's factorize this, and we have lambda s derivative of g with respect to s. So it becomes lambda s s minus 1 and derivative. So this is a partial differential equation of g with respect to t and s. So all we need to do here is to solve this partial differential equation. So it's partial differential equation, PDE. So let's do it. But to solve this equation, we need to have the initial condition. Okay, so when t is equal to 0, the number of bacteria is equal to n0, and so that's the initial condition. This translates into, in terms of the generating function, so g of s0 becomes this. So Pn of 0. So in terms of the probability mass functions, this is this Pn of 0 is equal to 1 if n is equal to n0. Otherwise, it's 0. So this should become Pn0 of 0, which is 1. Wait a minute. Which is P0. No, it's not 0. It should be because this summation starts from n0, so it should be s to the power of n0, which is equal, so this is 1, and everything else is 0, so that's s to the power of n0. So this should be the initial condition. Now we want to solve this partial differential equation with this initial condition. But how can we do that? First of all, what we want to do is to get rid of this term. Okay? Because if this is gone, then this partial differential equation can be solved very easily. So how shall we get rid of this? To do so, we change the variables from s to some another variable. Let's say z. So we change variables from s to z to get rid of this term. So this is how we do. So if this term, lambda s minus 1, can be expressed as a derivative of s with respect to the new variable z. Okay, so suppose this is the case. Then we can express this partial differential equation in this way. Del g del, sorry, this is not t, should be s. Okay, s. And if this is the case, then this becomes partial derivative of g with respect to z. Right? So this is the chain rule. So if we can change the variables from s to z by using this relation, then we can simplify this partial differential equation, which we will see can be solved rather easily. So let's first change this variable in this way. So to do so, we need to solve this differential equation. So this is the differential equation: ds dz lambda s minus 1, and which is easy to solve. So this is a separable differential equation. So here's the standard way: ds, so move this part, s, let's go with 1 minus s, so put negative sign here, just for a technical reason, and lambda, negative lambda, and dz. So we integrate both sides, and you can use partial fractions, and this should be equal to natural logarithm of s over 1s and minus lambda z. Okay, and we just set constant 0. So s should, if you solve this for s, then it is equal to 1 over 1 plus exponential lambda z. Okay, then we substitute this s into this. But to do so, let's define a new generating function q z t, which is the generating function where s is replaced with z. So that is, so s is this. So in this case, this is 1 over 1 plus e lambda z and t. Okay. So if we use this notation, then this original partial differential equation becomes it's equivalent to qzt differentiated with respect to t, and equal to the partial derivative of qzt with respect to z. for the reason we explained here. Okay, we change the variable from s to z. So this partial derivative of g with respect to z is here, this one. Okay, now how can we solve this equation? Okay, so it is already known that the general solution of this partial differential equation is something like this. Let's see. QZT is equal to some function, some differentiable function w of z plus t. Okay, this w is any function, any differentiable function. Okay, so any differentiable function of z plus t can satisfy this partial differential equation. You can check. So if you substitute this function, assuming this is differentiable with respect to z and t, then this is automatically satisfied. So if we put this, so let's see, we'll see that this is z plus wz plus t, t and wz plus t with respect to z. Okay, so so now we want to determine this function w based on the initial condition. Okay, the initial condition was g of s0 is equal to s to the power of n0. So this was the initial condition. Okay, so now we know s is equal to where is it? This. So we substitute this s into here. So that is, let's see, that is 1 over 1 plus e to the power of lambda s, lambda t. Wait a minute, is that lambda t? Lambda z. Lambda z, yeah, it should be lambda z. Lambda z to the power of n0. So this should be equal to w of z. So because t is equal to 0. So this is the function of z alone. And this should be equal to q of z0. So this function w should be of this form. Okay, so let's write it. W z should be equal to, so this is inside this parenthesis is just 1 over something, so that's 1 over 1 plus e lambda z to the power of n0. Okay, so w is this function. Okay, so this is determined from the based on the initial condition. Okay, then the generating function g of st is equal to q of zt, which is w of z plus t. Now the w is this, so we just replace this z with z plus t. That should be equal to 1 plus e to the power of lambda z plus t to the power of n0. But okay, let's split inside this exponential. So that is 1 over, let's write this way, 1 plus lambda e to the power of lambda z times e to the power of lambda t and 0. So this part is equal to, let's see, okay, from here, let's see, from this, you see, if you take the exponential of both sides, you have s over 1 minus s equal to exponential of negative lambda z. So from this, we can get rid of exponential of lambda z here. So that is 1 plus 1 minus s over s exponential of lambda t to the power of n0. Okay, so let's make it prettier a little bit. So this becomes, let's see, so let's see, it should be equal to s to the power of n0 exponential negative lambda n0 t over 1 minus exponential lambda t times s to the power of n0. Okay, so this is the final form of the probability generating function. But this is not as useful as we wish yet, because what we were interested in was the probability mass function. So let us expand this function of s into the power series of s. Okay, so I think you can use the negative binomial theorem. Okay, negative binomial theorem. So let's put, okay. So the numerator doesn't contain any, okay, oh, it does. Okay, so this part doesn't contain any s, so we just leave it alone. And the rest can be expanded in this way. Okay, first let's put s in here. And this denominator is m from 0 to infinity, and m plus n0 minus 1, n0 minus 1, and 1 minus e lambda t times sm. And move this s term inside. So let's see. This can be like n0 sum of n equal to n0 to infinity and n minus 1 m n0 minus 1 minus exponential negative lambda t times to the power of n minus n0 times s to the power of n. Okay, so this is quite a feast, and I think it's pretty complicated, but should be you should be able to uh, check this. So this is the power series expansion of this function, the probability generating function. So that means these factors represent the probability mass function for the number of bacteria at any time. So okay, so and the summation starts from n0, and after all, we should have Pn of t equal to n minus 1, n0 minus 1. So this is a combination, of course, and lambda n0 t and 1 minus exponential lambda t n minus n0. So this is, of course, for the case where n is greater than or equal to n0. And otherwise, the probability is 0 if n is less than n0. Okay, so this is the final result. Now that we know the general form of the probability generating function, we can calculate various expectation values. For example, the number of bacteria at any time, n of t. So let's calculate this expectation value. This is given by the derivative of the generating function with respect to s, evaluated at s equal to 1. So if you differentiate that function, where is it? This function, maybe this should, okay, let's take this one. So if you differentiate this function with respect to s, it's quite involved calculation, but you should find, after all, that this is equal to n0 to the power of exponential of lambda t. So this is an exponential function. Okay, and so if you plot this, so at time t equal to 0, the number of bacteria was n0. So from that point, it increases exponentially like this. And the rate of increase is, of course, lambda. So this is a very simple result and easily interpretable. So if nothing dies, only increases by birth or cell division or whatever at a certain constant rate times the population size at each point, then the population increase exponentially like this. So that's the main conclusion for the birth process. Okay, next let us turn to the death process, where individuals only die but not born. Okay, so suppose a population of some individuals, and each of the individuals may die with certain rate of probability at any time. Okay, so if the rate of death is mu per person per some unit time, then during time period of delta t, the probability that one individual dies is approximately this, mu times delta t. So if there are n individuals in the population, then the probability that someone dies within the population is proportional to the population size. So this probability should be multiplied by the number of individuals. And if everyone dies, then there will be no one left. So if there are 0 individuals in the population, then no one can die, so the population does not decrease anymore. So it will just stop at 0. And that's the end of this population. And since there are no birth, so it cannot increase, so anyone can die anymore. Okay, so let's formulate this problem. Again, in the same manner as the birth process, we first set up the differential difference equation. Okay, so to do so, we set up as usual, we use the partition theorem. So if there are 0, okay, so here's the random variable we are tracking, the number of individuals in the population. If there are 0 individuals in the population at time t plus delta t, it must be the case that at time t there are 1 individual in the population and it died. Okay, so there was 1 individual in the population. So this is the probability that there was 1 individual in the population at time t. Okay, so this p0 is the probability that there is no individual in the population at time t plus delta t. Okay, of course we are assuming that delta t is small enough that no 2 individuals die at the same time. Okay, and so this is one case, and another possible scenario is that there were already no one in the population at time t, so nothing happened and no one at time t. So if there are no individuals at time t, then with probability 1, in the next instance the population size is also 0, right? So this is probability 1. Okay, and if there are n individuals which is greater than 0 at time t plus delta t, then there are 2 scenarios. So first, there were n plus 1 individuals at time t and someone died. Okay, so this is one scenario, n plus 1 individuals at time t. Or there are already n individuals in the population and no one died during delta t. So that probability is 1 minus mu n delta t plus some small constant, which is greater order of delta t, and Pn of t. And we also need to consider a special case where the population size is at the same number as the initial population size, n0. Okay. In this case, at time t, there must have been n0 individuals and no one died. That's the only scenario, because the population size does not increase. So if there are the same number of individuals as the initial time, then nobody died. So that would be 1 minus mu n0 times delta t and Pn0 of t. Okay, so we have actually 3 equations here, where the population size is the same as the initial size, or the population size is 0, or somewhere in between. Okay, so this n should be greater than 0 and less than n0. Okay. And from these equations, I think you can already can derive the following differential difference equations. So that would be this dp0 of t dt is mu p1 t, and dpn of t dt is mu n plus 1 pn plus 1 of t minus mu pn of t, and dpn0 dt minus mu pn, oh wait a minute, it should be n0 here, and pn0 of t. So here are the differential difference equation to be solved to find out these probability mass functions. And wait a minute. What's the initial condition? Initial condition should be this: Pn0 of 0 is equal to 1. So this is the initial condition. Okay. Now let's solve these equations, and of course you can try direct method, but as we already know the method of probability generating function, let's use that method from the beginning. Okay, first of all, as usual, the PGF is defined as this. So in this case, the number of individuals varies from 0 to n0 because it can only decrease from n0 down to 0. Okay, so the summation is from 0 to n0, and Pn of t and s to the power of n. So this is the PGF. So as usual, multiplying both sides of this differential difference equation with the powers of s and sum over all the terms, you should have, let's see, something like this. So sum left hand side s to the power of n, and the right hand side there are two terms from 0 to n, 0 minus 1, and n plus 1 pn plus 1 sn. Oh, wait a minute. Pn plus 1 of t and s to the power of n. And minus mu and n from 1 to n0, and n pn of t s to the power of n. S to the power of n. So this is derived from the differential difference equation, and we want to express this equation in terms of the PGF. So if you look at this n plus 1 and s to the power of n, you can see that this is the derivative of s to the power of n plus 1 with respect to s, right? And from this n and s to the power of n. So how can we get rid of that? And s to the power of n is s to the power of n minus 1 times s. So move this s, 1s, outside of the summation, and this times this is the derivative of s to the power of n with respect to s. So, and of course, we can put this differential operation in to the outside of the summation, and so on. And after all, you should be able to derive this equation. So partial derivative of the PGF with respect to t is equal to mu 1 minus s, and the partial derivative of the PGF with respect to s. Okay, then we want to solve this. And again, just like the birth process, we want to solve this by first getting rid of this part. Then it's easier to solve. So that's what we do. And also the initial condition s of 0 is should be equal to s to the power of n0. So this is the same as the birth process. Well, anyway, change the variable. This can be done by setting, so change the variable from s to z, and this can be done by this ds dz equal to mu 1s, and solving this ordinary differential equation. You can get rid of s here. And after all, well, I don't show the details here, but you should apply the same methodology as before as the birth process, and finally you should have this result. G of st equal to, let's see. Okay, so this is the final result. And from 0 to n0, and n0 choose n exponential of n lambda t, 1 minus exponential, not lambda, it's mu t to the power of n0 minus n s to the power of n. Okay, so in the case of the birth process, we use the negative binomial theorem. In the case of death process, we use the binomial theorem. So it's kind of positive binomial, the ordinary binomial theorem. Okay, so if you look at this, it looks like this. Okay, maybe it's easier if you look at this way. So n varies from 0 to n0, and this coefficient is n0 choose n, and this one e to the power of negative mu t times s, everything, to the power of n, and 1 minus, wait a minute, maybe I shouldn't put s here, and 1 minus e minus mu t n0 minus n times sn. So look, this case, if you put, for example, p equal to e to the power of negative mu t, then this is 1 minus p, right? So this is exactly like the binomial theorem, and it's a binomial distribution, kind of. So after all, this is the probability mass function for the death process. So this is it. Now, from this result, you can calculate the probability of extinction at time t. So that is the probability that there are 0 individuals at time t, which is given by this is 1 minus e to the power of mu t to the power of n0. So let's see. So if you put n equal to 0 here, that is this probability. So this is the probability of extinction. And the probability of ultimate extinction would be this: the limit t going to infinity, probability of 0 of t. So this So if you put t equal to infinity, then since mu is positive, this converges to 1. So in this model of the death process, the probability of ultimate extinction is 1. So it's almost sure. But anyway, if you look more generally, if you look at this functional form of the probability mass function, you can consider this as a binomial distribution. Out of n0 initial individuals, n individuals are still alive. Okay, so n0 minus n means those who died. Okay, so it's like if there are n individuals, some are still alive, some are dead. So we can separate n0 individuals into live individuals and dead individuals. So this choice is like binomial distribution. Okay. Then if you look at this in this way, then what's the birth process? It was based on the negative binomial distribution, right? So let's go back. Let's see. This one. This one. So in this case, let's see. This n minus n0 is the number of cell divisions. Okay, individuals that came as a result of cell division, right? And n0 is the number of individuals in the initial population. So this is like the negative binomial distribution where given the number of initial individuals, how many individuals are derived by cell division. So this n is the random variable. So this is the negative binomial distribution. Okay, so now we know the birth process and the death process, and now we'd like to combine these two. So we have seen that the birth process is defined by these differential difference equations, and the death process defined by these differential difference equations. And now we combine these two so that each individual in the population can divide into two individuals, or it can die. Okay, so there can be birth and death at the same time. So the birth rate is lambda, and the death rate is mu. Okay, so if we just combine these two, just add these terms with these terms and these terms with these terms and this. Okay, and so let's see. First, when n is equal to 0, so consider this case. Okay, so that would be just dp0 plus dt, and so this state, so no individuals, this can be reached only from the population size of 1. Okay, because if the number of individuals is 0 in the population, there is no cells that can divide to give a birth to a new cell. So this is the only possibility for n equal to 0. Okay, for other values of n, we combine this one and this one. Okay, so that would be Pn of t dt. So in this case, we have, let's see, Pn here and Pn here, and both are proportional to n, and they have different coefficients. And we have n here and n plus 1 here. So they are of different terms. So first, let's combine these two. So that would be negative lambda plus mu times n times Pn of t. And the term that is proportional, oh wait a minute, this is n, this should be n minus 1 here. Okay, right? Yeah, n minus 1. So so n, the term involving n minus 1 is plus lambda lambda n, wait a minute, n minus 1 and Pn minus 1 of t, and the term involving n plus 1 is mu n plus 1 and Pn plus 1 of t. And what about the initial population size? This one and this one. So these are actually included in the case of this, because if we combine both birth and death, then this initial population size is nothing special. So even if the initial population size can be greater than n0, and if someone dies, then it can go back to the initial population size. And even if the population size is less than, if the population size is less than the initial one, but still someone can born to, so that the population size goes back to the initial population size. So there's nothing special about n0 in the present case if we combine both birth and death. So these two differential difference equations should be sufficient to describe the birth and death process. Now I guess you know what to do. Okay, so we define the PGF g of s and t as from n equal to 0 to possibly infinity, because it can, cells can divide indefinitely, or it can become extinct. So the number of cells is from 0 to infinity. So Pn of t times s to the power of n. So this is the probability generating function. And by the usual procedure, we convert this differential difference equation into the partial differential equation of this PGF, which is found to be this. And I think you can easily derive this. So this is the partial differential equation we're going to solve now. It's with respect to s. Okay, and I hope you already know by now how to solve this, right? So get rid of this factor by appropriate change of variables. Okay, however, we have to be careful about the relative magnitudes of lambda and mu. Okay, first case, let's say case 1, is where lambda is different from mu. Okay, in this case, you can just apply the previous technique, and the result which you should be able to get easily is given by this. It's a little involved. Mu1 minus s minus mu minus lambda s, and exponential minus lambda minus mu t over lambda 1 minus s minus mu lambda s, exponential of lambda minus mu t and to the power of n0. So this should be it. And yeah, you should derive this. Also, you should see that if mu is 0, so in this equation, if you set mu equal to 0, then it should become the same PGF as the birth process. And if you set lambda equal to 0 rather than mu, then it should be the same as the PGF of the death process. Okay, can you see that? But anyway, so this is the result. So if you expand this in the powers of s, then you should get the probability mass function. So all the pn's, right? But that is very tedious, and I don't recommend it. But the real beauty of PGF is that we don't have to know these mass functions in order to calculate important quantities such as the expectation values. For example, this expectation value of the number of individuals at any time can be calculated by differentiating this g with respect to s, then substitute s for 1. So that's this 1t, oh, not s, but here, ds, and this should be n0 to the power of lambda minus mu t. So if you look at this equation, this is very familiar. This seems familiar. If mu is 0, then this is the result we have got for the birth process, which is just exponential increase of the population size. And if you put lambda equal to 0, then this is the probability of non-extinction, that is probability of survival in the death process. So if lambda is greater than if lambda is greater than mu, then this is an increasing function. So the population size will still increase exponentially starting from n0. And if lambda is less than mu, then the population size decrease exponentially starting from n0, which is reasonable. And you can also calculate the probability of extinction. I hope you try this. And also the probability of ultimate extinction, that is the limit of this with t going to infinity. Okay. And the next is the case where the values of lambda is equal to that of mu. So this case must be treated specially because in the partial differential equation, if lambda is equal to mu, then this part is like lambda s minus 1. So if you factorize lambda out of this, then we have s minus 1 here also. So it will be s minus 1 squared. So if you want to get rid of this factor, then of course you set up some ordinary differential equation with a new variable, but the solution will be different. It doesn't involve logarithm anymore. So this should be treated specially. And yeah, you should solve this somehow. And the result should be this. And 1 plus lambda t minus 1 and 1 minus s over 1 plus lambda t 1 minus s, and everything to the power of n 0. Okay, so since lambda is equal to mu, we cannot change one of them freely. Okay, so this is the result. And of course, from this you can calculate the expectation values, such as this. So, and please try to compare this result with case 1. Okay. Anyway, you should notice that in any case, the result is some power to the n0, right? So something to the power of n0 in case 2, and it was the same for the case 1, right? It's something to the power of n0. So why is this the case? So here's one alternative interpretation of this problem. So here, first of all, the original definition of the probability generating function is this. It's the expectation value of s to the power of that random variable n of t. Okay. Now, let us decompose this random variable into several summation of these: n1, n2, up to n0 of t. So each of these is a random variable, and ni represents the number of descendants, so number of offsprings or descendants of individual I. Okay, so there are initially n0 individuals in the population. So each of these may produce offsprings, and those offsprings produce yet other offsprings, and so on. So we can construct the genealogy of each individual, and this ni represents the number of all descendants originated from the ith individual in the initial population. So the total population at any time can be decomposed into the sum of these number of descendants of each individuals in the initial population. Okay, and we are assuming that those individuals are behaving independently. There are no interactions between them. So therefore, this probability generating function can be expressed in this way. So g of st is the expectation value of the power of s to the power of n1 plus n2 plus and so on. So we just split this s to the power of n1 and s to the power of n2 and so on. But each of these are independent. Each of these is independent from others. So we can split this expectation value of the product into the product of expectation values. Okay. So this is possible because these are all independent. So, but not only they are independent, but they are also identically distributed. So they behave exactly in the same manner, meaning they follow the same probability distribution. Therefore, we can replace this product. So each of them should be identical to others. So it should be expectation value of s to the power of n1, for example, to the power of, so there are n0 factors, so it's power of n0. That's why all the generating function has this exponent n0. We can consider more general population processes. For example, uh, like this, P0 is determined by lambda 0. So this constant actually depends on, it's not a constant, it can depend on the number of individuals and time. So this is a very, very complicated process. So the rate of death can depend both on the population size and time. You get the idea. Uh, so this will be lambda n minus 1 and t, and lambda n mu n both depend on time, and mu n plus 1. So everything can depend on both population and time. This is extremely complicated process. And of course, unless we specify the functional forms of this, there is no possibility that we can solve these equations. Yeah, so depending on the problems, we change these functions. So far we have just assumed that these constants, these coefficients do not depend on time, but they're just proportional to the population size. Okay, so that was uh, this is the most general form of these population processes, but in general we cannot solve them. So even if we can specify the function forms of these coefficients, it's usually the case that we can only solve this numerically by using computer simulations. So that's all about the birth and death processes.